Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani. I am from Department of Computer Science, Ayurved College, University of Delhi. So in our previous lecture we have seen the concept of threads as well as its advantages over the process, and today's agenda is we will be continuing with the threads, and also we will be looking into system calls. Threads we have seen it's a lightweight process in the execution, and one kind of we can say process can have multiple threads. So within the threads we can have two types of threads, which is one is kernel level thread, another one is user level thread. Now when we consider types of threads, we have kernel level threads and user level threads. And what is kernel, that we have already understood when we started the process, when we started a lecture series of operating system concepts. So now let us try to explore these both these types of threads. Let us begin with user level threads. So user level threads, it's very important to note that your operating system is not going to recognize this user level threads. Now the question which comes up in the mind, then who is going to recognize this user level thread, and how it is going to we can say matter for us or matter for a system to have a user level thread. Why one should have a user level thread if it is not even being recognized by operating system, as your operating system does not recognize the user level thread. But the user level thread, the advantage with the user level thread is it can be easily implemented by the user. So now please try and understand that we have a process, and within that process, if we want to achieve the parallelism, user with its own programming can program the thread, and it is very simple to program these threads in many of the programming languages which are available nowadays. So for example, let's say Java. So Java is having its own libraries and its own setup of multi-threading. So it is the kind of we can say it is the prerogative of the user when it needs some kind of multiple threads going on, or some kind of we can say parallelism, then user can implement the user level thread, although operating system is not going to recognize these user level threads. But a main thing which is worth noticing here is if a user performs a user level thread blocking operation, the whole process is being blocked. It's not that only one thread is going to be blocked, which is in the case of kernel level threads. We will be seeing it in a short while. If a user performs a user level thread blocking operation, the whole process is going to be blocked. And while if we talk about kernel level threads, they don't know anything about the user level threads, because user level threads are in execution within their own address space, within their user address space, while kernel level threads are getting executed within the kernel space. And the kernel level thread manages the user level threads if they are single threaded processes. So for example, these user level threads are being managed by kernel level threads, but again these kernel level threads are not going to we can say witness or not going to acknowledge the multi-threading of user level threads. The kernel level thread is going to treat the user level thread while managing them as if they are single threaded process, and we can see very common examples of these threads in Java. Now coming to what are the advantages of user level threads. So one is, as I have told you, that a kind of set of libraries or a whole set of implementations is available within the individual languages as well. So ease of implementation, we can say a user can with its own programming, a user can have the task of multi-threading implemented with the help of user level threads. So implementation ease is one of the advantages. Then we can say it can be applied to such type of operating systems that do not support threads at kernel level. So for example, we have some operating systems for which your kernel level threads are not being supported. So in that kind of situation, if we are looking for multi-threading or this multiple things to be going on simultaneously, then the only solution which we are having is the user level thread. Also, user level threads are faster and efficient, we can say, in order to be executed. Also, context switch time is shorter than kernel level threads. So in the previous lecture we have seen that the context switch time is actually shorter in threads when we compare with the process. So process is going to take a lot more context switch time, while your threads are going to take a little lesser. While within the threads, if we talk about user level thread and the kernel level thread, so context switch time of your user level thread is relatively shorter as compared to kernel level threads. Also, user level threads does not require any modifications of the operating system, and on the contrary, they are even not recognized by the operating system. So they are having ease of simple representation, ease of implementation. They also have faster context switch time. Then the register, program counter, PC, stack and many thread control blocks are stored in the address space of the user level process. So within the address space of the user level process, the value of registers, the program counter, stack and many thread control blocks are stored there. And as we have seen, it is very simple to create a switch and synchronize threads without the intervention of the process, and this you can find very easy in many of the languages. I am giving the example of Java, because multi-threading is very easy and very efficient, and it can be easily implemented in Java. So it is going to take very little effort in order to create or in order to switch and synchronize between the threads without the intervention of the process. This can be easily done. So these were the kind of, we can say, we tried to understand what is the user level thread and what are the advantages of user level threads. Coming to its disadvantages, we have some disadvantages when we talk about user level threads as well. So these threads lack the coordination between the thread and the kernel, and as kernel level threads, even if they recognize user level threads, they will be recognized as a single entity, as a single process, not in the form of multi-threading. So that is one a disadvantage, that user level threads lack coordination between the thread and the kernel. If a single thread among all the let's say n number of thread, if a single thread is going to cause a page fault, then the whole entire process is blocked. Even if the page fault is being caused by a single thread, the whole process is blocked. So here in the figure you can see the structure of user level threads operation. So here is a user level thread which is kind of directly interacting with the system calls, and even if one of the threads is being blocked, the whole process is completely blocked. It's not about the one particular event or one particular execution unit of the process is going to block. No, in case of user level threads, if a thread is being blocked, then the whole process is also blocked. Now coming to the kernel level thread. So till this point we have seen what is the user level thread and how are we going to implement and use this. Kernel level thread, they recognize the operating system, they are we can say in gel with the operating system. There is a thread control block and process control block in the system for each kernel level thread and each process in the kernel level thread. So there is going to be a thread control block as well as a PCB within the system for each thread and process which are operating within the kernel level thread. Kernel level thread is very important. The difference between the kernel level thread and user level thread is very important, that kernel level thread is implemented by the operating system, while the user level thread is being implemented by the user through its own programming. Kernel level threads are kind of well recognized by the operating system. Also, we can say that the operating system kernel knows about all the thread, and kernel is the entity which is going to manage them. Then the kernel level thread offers a system call to create and manage the threads from the user space. That means the threads which are available in the user space are to be managed by the kernel level, and this whole management and creation can be done with the help of system calls. We have separate system calls there, and we will be we can say witnessing the system call and its meanings and all that within a short while in the lecture. Also, we can say the implementation of kernel level threads is more difficult than the user level thread, and also the context switch time is longer in case of kernel threads. So we have seen that context switch time is shorter for the threads as compared to the process, but when we compare within the threads, when we compare kernel level thread and user level thread, the context switch time is more in, or we can say it is longer in the kernel thread. So here is a figure which is going to give you clear picture of the kernel level threads and the user level threads along with their address spaces. So here you can see that we have a process P. Within that process P, the kernel, there are 3 kernel level threads which are being shown in the figure, and these kernel level threads are operating inside the kernel space, and your process is we can say kind of well aware of or is in the gel with all the kernel level threads. While if you can see the upper part of the figure, the user level threads are operating as separate entities within the user space, and your kernel level threads are something which are if you can see here, are connected to user level threads. But even then, all these user level threads are taken as one process, or we can say as acknowledged as one user level process, even if they are having multiple threads. Apart from that, let us try to explore that as compared to the user level threads, are there any advantages of kernel level threads? So yes, we can say yes. These kernel level threads are fully aware of all the threads, as you can see in the figure, that these are in gel with the process, and these are also in gel these are also in we can say sync with the user level threads. So yes, kernel level threads are fully aware of all other threads which are operating inside the system, and kernel level threads are actually good for those applications that block the frequency. While we have seen in the user level thread that user level thread, if one thread, even if it is going to we can say block, the whole process will be blocked. But the kernel level thread is much more suitable for blocking the frequency. Coming to the disadvantages of kernel level threads, is kernel level threads manages and schedule all the threads. So kind of we can say a complexity or a flavor of complexity is automatically inserted when we talk about the implementation of kernel level thread. So the implementation becomes kind of we can say difficult, and because of this difficult implementation and more complex management, these are slower than user level threads. So these are the advantages and disadvantages. Now let's see some more differences between the user threads and the kernel threads. So user threads, as we have seen, are implemented by users, while kernel threads are implemented by operating system. Now the next parameter of the difference is about the recognition. Operating system does not recognize user level threads. These user level threads are well recognized by kernel threads but not directly by the operating system, while the kernel threads are recognized by the operating system. Implementation, as we have seen for user level threads, it's an easy implementation, while the kernel threads are more complicated, we can say, as far as implementation is concerned. Context switch time is less for user threads, while for the kernel threads the context switch time is much more. Then hardware support, as we try to explore the aspect of hardware support, we can see that user threads, in case of user threads, context switch, if we are talking about, that requires no hardware support, while kernel threads, if are switching the context between them, then they need a hardware support. Blocking operation, if we talk about, then entire process will be blocked in case of user threads, even if one thread is blocking the process, while this is not the case in case of kernel threads. Or if one thread is blocking the process, other threads can continue the execution. Now please try to link that why it is happening, because your user threads are considered as a single entity, not the multiple threads by kernel threads who are going to recognize them. So kernel threads are going to recognize the user threads, not the operating system. That is the first thing. Then even after recognition, these kernel threads are going to take these user threads as one entity, not as the kind of multiple entities. So if even one thread is going to block the process, one thread is going to be blocked, the entire process will be blocked. While if we talk about kernel threads, another thread can continue the execution. As we have seen that implementation is easy in case of user threads, and for kernel threads it is more complicated. Similarly, the creation and management is easy as in case of user threads, and for kernel threads it is more complicated. So with this understanding of user threads and kernel threads, let us switch to our one important subtopic of this particular lecture, which is about system calls. So when we say that our programs or our set of instructions, we can say, are going to interact with the operating system, the bridge between the programs and the operating system is nothing but a system call. A system call is a way for programs to interact with the operating system, or we can say it is a programmatic way in which a computer program requests a service from the kernel of the operating system on which it is being executed. So we are aware that our computer program is going to be executed onto the kernel, and there will be various services which a program is going to ask the kernel for its smooth execution. So the way in which your computer program is going to request a particular service which it needs from the kernel of the operating system, that programmatic way is nothing but a system call. So basically a computer program is going to make a system call when it is going to request the operating system's kernel for any type of service it needs. So system calls, basically we can say, it provides the services of the operating system to the user program via API, which is nothing but application programming interface, and it also provides an interface between a process and operating system to allow user level process to request services of the operating system. So the bridge between, or the interface, or we can say a platform between the process and the operating system is nothing but system calls, and system calls are the only entry points into the kernel system. So the program which is looking for some resources and it needs to communicate with the kernel, all the programs needing resources must use the concept of system calls. Then we see that we have seen, the services will be provided through system calls. What kind of services we are talking about? So here the services which we talk about is of process creation and management. Then we have the management of main memory, file access, directory and file system management, handling of various input output devices, providing the protection, and facilitating the networking. So all the services which we can say are provided by the operating system. The bridge, again I am saying that the bridge is the system calls. All these services will be communicated with the help of system calls, or will be asked by the program with the help of system calls. So these system calls are divided into 5 different categories. One is of process control, which is kind of creation, ending, aborting, terminating, allocating the free memory to a particular process or any other resources. Then we have file management. So for creation of file, for opening of file, for closing, for deletion and for reading the file, we have separate system calls. For management of various input output devices, that is allocation and deallocation, we have separate system calls. And also we have calls about the information maintenance and communication. So here you can witness some examples of the calls which comes under the process control. So for Windows it is create process, exit process and wait for a single object. For Unix it is for creation is for, then we have exit and wait. Similarly for Windows, if we talk about file manipulation system calls, we have create file, read file, write file and close handle, while in Unix we have open, read, write and close. Coming to the category of device manipulation, in Windows we have set console mode, read console and write console, while in Linux we have IOCT, then we have read, then write. About information maintenance, we have get current process ID, set timer, sleep in Windows, while we have get PID, alarm and sleep system calls in case of Unix. Communication, when we talk about, it is having create pipe, create file mapping, map view of file in Windows, while in Unix it is having pipe, SHM get and mmap. In case of protection, it is set file security, initialize security descriptor, set security descriptor group, ch mode, umask and ch own, which is regarding permissions in case of Unix. So these are just the names or the examples of system calls which are available under various operating systems through which a program can communicate to the kernel. So within this lecture we have seen the difference between user level threads and kernel level threads along with their advantages and disadvantages, and we have also seen the concept of system calls along with the definition and its various example. Here is a list of references which is being sought for the preparation of the lecture. Hope you have enjoyed it. Thank you for a patient hearing.